Hello everyone, welcome back to your own channel, Theoretical Condensed Matter Physics. And this is our Be Smart in DFT lecture series. And here, now, we are with lecture number 6, Nuts and Bolts of DFT, part 2. Okay, as was promised before also, the aim of this lecture series are to make you really smart in your research and to make you so efficient that you can interact knowledgeably with your collaborators. And also, after finishing this particular lecture series, your package manual will express itself in a much familiar way. Well, in our previous video, we had discussed one key point of DFT calculations, that is the K points. In this particular video, we will try to understand two other major and basic aspects of DFT calculations, that is the cutoff energy and the pseudopotentials. Okay, let's take this car for today's ride. Ugly, right? I hope this color is okay for you. Okay, let's make it colorless and simple. And now this is a too simple car to ride, isn't it? But if I ask you to write a mathematical equation that will describe this simple curve, which has the form of a car actually, will it then also be a simple task only? I guess not. To do this job, that is, describing this curve with a mathematical equation, we can take a much simpler mathematical form, a circle. Let's put these circles in different coordinates to somewhat mimic this curve. That's okay. But if we remove this curve, that is, if we remove the outline with circles alone, we can't pretty much argue that this is a real good representation of the curve, right? So, two main points are the sides are too curved, and secondly, the window of the car is missing. Okay, no big deal. You are intelligent and you may say that, well, what if I use two types of circles of different radii, of course, to describe the car? Okay, it's better now. In the next step, let's take four different circles. It's now quite a good representation of the car, right? Now these circles, these are called the basis sets, okay? And the outline of the car, what we tried to represent using these circles or the basis sets, we can relate this outline of the car to the real wave functions. Okay. Now, what are the basis sets that we can use to describe the wave functions? Definitely, we will not use the circles there, right? For that, that is to describe the wave function, we may start with two different countries, United States and Germany. Okay. No, not that. Here we are with two astounding scientists from two different countries and two different timelines also. Carl Friedrich Gauss and John Clark Slater. Or more precisely, what we are going to talk about here are the orbitals resulting from their equations, commonly known as Gaussian Type Orbitals or GTO and Slater Type Orbitals or STO. GTOs vary as e to the power minus alpha r square, whereas the dependence of STOs vary as the exponential of negative alpha r. Of course, alpha is just the exponent, right, which can take different values. Now, let's take a look at the 1s orbital of the hydrogen atom. It has the form as psi 1s equal to pi by root 2 exponential of minus r by a0, where this a0 is the Bohr radius and has the value of 0.529 into 10 to the power minus 10 meter. Of course, every one of you know that, right? However, clearly it's a Slater type orbital, right? And not Gaussian. And but one is trivial. Now take a look at these wave functions. It's right that all these have the form of exponential of minus alpha r, but there are other dependencies on r too. In fact, if you look at these plots, that is the plot of the orbitals, radial nodes can be seen in some orbitals, which cannot be reproduced by one Slater type orbital. Therefore, the message is that the STOs are not perfect either. That's okay. But remember that always Slater type orbitals have the correct functional behavior near the nucleus, that is, a cusp and a decay in the correct way at long distances. Gaussian type orbitals provide a relatively poor description of the atomic orbitals. They have a finite value at the nucleus and decay too quickly, and thus it underestimates long range interactions. However, though there are some deficiencies, in both cases, there is actually no loss in desired accuracy as long as enough of these new functions are used, such that there is an adequate description of the final molecular orbitals. So both the STOs and the GTOs stand on an somewhat equal footing now. Though yes, up to now, STO is silently getting a little advantage over the other one. One thing is there, remember, we may use one or the other of these functions as the basis functions, but we never ever will mix basis function types. I hope up to that part everything has been clear to you. Now we need to check one other important property too of these basis functions. See, what you are going to do it in your computer, right? So we need to check how much these functions cooperate computationally. For that, we are going to need the works of a famous physicist. You may recall that our very first talk of this particular series started with Walter Kohn, right? The father of DFT. However, today we are not going to talk about him, but the one with whom his Nobel Prize was shared, Sir John Anthony Pope. Another two physicists who also did pioneering work with Sir Pope in this particular field are Warren J. Hare and Robert F. Stewart. In their 1969 paper titled Self-Consistent Molecular Orbital Methods, Use of Gaussian Expansions of Slater type atomic orbitals, they have shown that the Slater type orbitals can be represented as a sum of Gaussian type orbitals, and the efficiency of such representations are very high than actual Slater type orbitals. You may take a look into this paper. I'm putting the link in the description box. However, let me explain one important aspect of this. See, while doing DFT calculations, often we are going to encounter these type of integrals. Here, f1, f2, f3, and f4 are the functions for the basis sets. This particular integral is called a four-center integral. Now, the product of any two Gaussians is just another Gaussian, and the sum of two Gaussians is easily evaluated. Thus, this particular integral easily reduces to a two-center integral when we use Gaussians. But this is not the case for STOs. The product of two STOs is not just another STO, but the complication to evaluate the integral of the product is actually multiplied while using STOs. So, in conclusion, I may quote one particular sentence from that famous paper. The smaller Gaussian representations seem suitable as universal atomic orbital basis functions, which may be used in molecular calculations instead of STO sets. In today's time, though, some ab initio packages are there like STOP or SMILES, which use Slater type orbitals for calculations. But most of the packages prefer the Gaussian type orbitals. Now, just one little thing about the nomenclature of GTOs. But before that, tell me, what do you think? How many Gaussians are needed to represent a typical STO for a good enough approximation? Please watch this video now and write your case in the comment box if you are seeing this video for the first time. I just actually want to see how synced are we as when I first learned about this. I thought for a good enough representations, we are going to need at least 20 GTOs or 50 or 100 would be better. But do you know the real number of GTOs? Often only 3 GTOs are more than sufficient. Now, if we represent one STO by 3 GTOs, then in short, this sum is called STO 3G. Similarly, for n GTOs, it is called STO NG. Okay. Actually, there does come a point where the Gaussians become linearly dependent, and then adding more functions is not useful anymore. In fact, in that 1969 paper, they particularly said the STO3G set in particular is very economical to use, and as a minimal, that is 1s, 2s, and 2p basis, can be applied to a quite large organic molecules. However, STO6G is too greatly efficient that we really can rely upon and stop adding any more Gaussian to it. Okay, okay. Enough about these basis sets. Maybe we can discuss more in some other lecture about these basis sets. But for now, let's move one step front. The very famous and that we have used also many times, the Bloch's theorem. The solutions of the Schrodinger equation for a supercell have the form psi k of r equals to exponential ik dot r uk of r, where uk of r is periodic in space with the same periodicity as the supercell. By the way, if you are not getting the terms supercell and these things, please follow the lectures that I have done before in this series. Okay, there I have mentioned what is a supercell and other things. Okay, it is now time to look at this part of the problem more carefully. The periodicity of uk of r means that it can be expanded in terms of a special set of plane waves. To be precise, in mathematical form, uk of r equals to summation of a g cg exponential ig dot r, where the summation is over all vectors defined by g equals to m1 b1 vector plus m2 b2 vector plus m3 b3 vector with integer values for mi, and b1 b2 and b3 are the reciprocal lattice vectors. Formalities are done. Now, using this expression for uk, psi k becomes summation of a g ck plus g exponential ik vector plus g vector dot r. Now, this expression brings a serious problem with it. It tells us even if we want to evaluate the solution at just a single point in k space, it will require the summation over an infinite number of possible values of g. And this does not definitely sound too promising for practical calculations. Lucky for us, this equation does have a simpler interpretation as the solutions of the Schrodinger equation. They are the solutions with kinetic energy, that is, E equals to h square by twice m k vector plus g vector modulus whole squared. Fine. Let's pause here and definitely remember this particular expression. Okay. But let's pause here and get back to our car example again. How many types of circle are needed to describe this car properly? Tell me. For sure, the complexity and the detailing of the car gets better as I use more and more circles. Now, if I label each circle as a function fi, then the shape of the car can be described as a sum of circles, the centers of which are determined by some coordinates x, y, and the size of which can be varied by the coefficient ci. In the language of mathematics, it becomes car equals to summation over ci fi of xy. Notice that total number of circles are too many, but different types of circle are described by different fi of xy, right? Okay. Ideally, we are going to need an infinity types of circle to describe the car accurately. But is it practical? No, absolutely not. Depending on what exact accuracy you desire, you may take only a few types of circles for the use. However, taking infinity amount of circles will literally take forever just to be drawn only. Isn't it so? Well, so the moral is you should take only a finite basis set to describe the car, or more precisely in our case, to describe the wave functions. At this point, I am consciously skipping a few mathematics, the finite difference method and the first Fourier transform, as they will be too mathematical for our purpose. But of course, I won't skip the essence anyway. Clearly, to perform the calculations in a computer, you somehow need to implement the wave functions quite in a systematic way so that your computer can understand the wave functions, right? Actually, what happens is the wave functions are represented as the integrals that are approximated with an equidistant grid of k vectors with identical weight, or you can say numerical grids. Obviously, from intuition alone, you know that the spacing between the grids, let's say dx, must be sufficiently smaller than the wavelength so that the representation of the wave functions become good enough for reliable outcomes. If you are not getting this particular point, please pause here and think for some time whether dx should be sufficiently smaller than the wavelength or not. Okay, actually, dx is like the pixel size of a picture. Now, as smaller are the pixel size, greater will be the clarity of the picture, right? And here the wave functions. Smaller the dx, better is the representation of the wave function. Therefore, adding energy, or in other words, high frequency and thus smaller wavelength plane waves, will therefore require increasingly finer grids to be described, which will quickly increase your computational cost. But in reality, as we also have seen in the car problem, the high frequency plane waves will only give very minor improvements to the results. But of course, definitely we cannot use too much small number of waves so that the result becomes too unreal. So, what is the way out here? Clearly, we need a bargain, right? I hope that particular scene from the movie Doctor Strange is very much favorite of you all. Okay, now at this point, we need to do a convergence test for the cutoff energy, just as we did for k points in our previous video. Okay. Here is a result from computing the total energy of FCC copper with different energy cutoffs of basis sets using quantum espresso code. We only have two axes here. One is for the value of the used energy cutoff for the basis set, and another for the total calculated energy of the supercell per atom for FCC copper. Okay? Well, as you can see, after 70 read work, the result is pretty well converged, and hence we can take E cutoff equals to 70 read work. Now, as the calculations have shown, it is reasonable to expect that the solutions with lower energies are more physically important, and we can safely thus truncate the infinite sum there to include only solutions with kinetic energies less than that cutoff that we have got by the convergence test. So, E cutoff becomes h square by twice m g cutoff square, and consequently the infinite sum then reduces to psi k of r equals to summation over g plus k modulus is less equals to g ck plus g exponential I k vector plus g vector dot r vector. Well, just as we shared for the k points also in our previous video, it is a good practice to report the cutoff energy also that you have used in your calculations to allow people to reproduce your results easily. Now, the cutoff energy, that is this E cutoff, in many ways, this parameter at least seems easier to define than the k points, as most of the DFT packages will apply sensible default settings if no other information is supplied by the user. But obviously, it is not what we recommend everywhere. For example, there is this one common situation where it is really unwise to blindly accept the default values for the cutoff energy. In most of the DFT packages, a default cutoff energy is assigned for each element. And if you have a supercell with different elements, the overall cutoff energy of the supercell will be the same as whichever atom in the supercell has the largest cutoff energy. I hope that particular rule of most of the DFT packages is clear to you. Now, let's try to understand this with a real scenario when the problem actually arises. Suppose, for a particular calculation, you need to compare the energy differences between the Cu atom and the Pd atom with their alloy CuPd. For instance, take that the default cutoff energy for Pd is greater than that of Cu. Okay, then what will be the cutoff energy in the calculation of the energy of CuPd? Obviously, it will use the cutoff energy of Pd since we have taken that its cutoff energy is higher than that of Cu. However, when the energy of Pd will be estimated, then also the code by default will use the cutoff energy of Pd. That's good. But the problem arises in case of Cu. When you are calculating the energy of Cu alone, the cutoff energy that will be used by the code will be the default cutoff energy of Cu, right? Now, since all three supercells are not using the same cutoff energy, a systematic error will be introduced, which is definitely undesirable, right? See, whenever you are comparing something, at least if you are having a neutral viewpoint, you should keep them on the same foot, right? Now, if you are using different cutoff energies for different supercells, obviously they will give different results. Even if for one particular supercell, if you are using two different energies, they will give different results. So comparison will get an error there, right? Then finally, the moral of the story is do not follow the default values of the cutoff energies blindly. So, we have talked a lot about wave functions, their frequencies and wavelengths. And it's time to check how much exactly these wavelengths are. It's a plot for Kohn Sham electron wave functions of an isolated silicon atom. As you can see clearly, the tightly bound core electrons in atoms are associated with wave functions with a shorter wavelength. Actually, not only the core electrons, but also the valence electron, that is 3s. Its wave function near the nucleus is also of shorter wavelength. Now, these oscillations actually often become comparable to the value of the cutoff energy that is generally taken in nowadays DFT calculations, and hence the chance of getting error increases. Remember, we have talked about that the cutoff energy or the frequency should be higher, or consequently, we can say that the dx, that is the pixel width for your wave function, should be much less than the wave function, not comparable to the wave function, right? Therefore, to include those oscillations, the cutoff energy should become much higher, and definitely the computation cost would then have increased proportionally. Obviously, scientists have developed tricks to bypass this particular problem, and the method to do so is called the pseudopotential method. Once upon a time, well, maybe not that ago, but long before the emergence of DFT in 1916, Lewis had shown that the valence electron will be most sensitive to the changes in the chemical bonding environment, while the core electrons, that is, which are located near the Coulomb singularity, will be relatively immune to such changes. And obviously, now it's an well established empirical fact too. Well, not only that, also, if you look at the electron densities, that the valence charge density peaks at a radius corresponding approximately to half the silicon-silicon bond length in silicon, while the core electrons are localized near the nucleus. Hence, moral is even the charge densities peaks at different points for different types of electrons. The core electron density is negligible where the valence electron density is large, and vice versa. Therefore, there is actually no reason that we cannot separate these two types of electrons, and we should be able to perform DFT calculations by keeping the core electrons as they appear in the isolated atom. That is, the properties of the core electrons are then fixed in all the subsequent calculations. They are not actually changing, right? This approach is called the frozen core approximation. But does it really help? Let me give you an example. In case of tungsten, we have total 74 electrons. Guess how many electrons are needed to be described with fusion core approximation? Well, it's only 6 electrons. Hence, clearly, the fusion core approximation leads to a substantial computational saving. That was good. But the next question then becomes, how do we decide which wave function should be considered core and which ones as valence states? As a rule of thumb, in the context of DFT calculations, the term valence corresponds to the outermost shell of the atom in the periodic table. For example, for tungsten, we would have 6s2 5d4. However, there are cases where one might need to include more electronic states in the set of valence electrons. For example, in case of bismuth, it is important to describe on an equal footing both the nominal valence shell 6s2 6s2 6p3 and the semi-core shell 5d10. In practice, the distinction between the core and the valence electrons is not a strict one and depends on the level of accuracy that one is trying to achieve. When in doubt, an inspection of the spatial extent of all the atomic wave functions might help. Take this figure, for example. By looking at the spatial variations of the electron densities, we can easily distinguish the core and the valence electrons. Still, if in doubt, you can definitely just mail me at thrtclcmp@gmail.com, or you can ask your respected supervisor. Okay, now once we got the idea of the deciding factor of which electrons should be considered as the valence states, the next question becomes, what is the procedure for eliminating the core electrons, right? For a start, see carefully. Near the nucleus, 2s state changes sign. That is, it exhibits a node in the region where 1s state is localized. And now come to 3s. The 3s state changes sign twice. That is, it exhibits two nodes, so that the overlap integrals with the 1s and the 2s state vanish. Maybe I should become more careful here. See, the wave functions that are having such nodes are actually the visualization of a quantum mechanical phenomena. All of you must have read that the wave functions are mutually orthogonal. That is exactly what is happening here. That's actually why, to preserve that particular property of the wave function, they do exhibit the nodes. Let me show you one. See, the integral of overlapping of 2s and 3s is 0 from the picture itself, right? You can try the others and also for other materials on your own, and it's really fun to do so. Okay, let me go back to DFT. See, if we simply ignore the core states, then we will also lose the information about the valence electron wave function in the core, right? But also, one fact is that too, if we try to obtain the correct oscillating features of the valence electron wave functions in the core, then it would be very difficult to describe them using a real space grid that we have obtained by introducing the energy cutoff. Since the wave function of the valence electron itself is highly oscillatory near the core, the representation of these oscillations would be very poor using the grid that we have agreed upon, and thereby it will underestimate the accuracy and the numerical stability of the calculations. Here in this picture, you can see actually how the wave function would look like using the grid that originates from a lower energy cutoff. Of course, one way out here is we may try to fix this issue by using a finer real space grid, or in other words, a higher energy cutoff. But the sole purpose of us is to reduce the computational cost by using a lower energy cutoff, right? So, the main problem that is arising here is because of the high frequency of the wave function near the core, or more technically speaking, more the nodes of the wave functions, less will be the accuracy if the grid spacing remains constant. I hope that is clear to you. Up to that point, no confusion is there, I guess. Therefore, what we will do here is we'll replace the real wave function by a smooth and nodeless curve in the core region, as shown in this figure. You can clearly see the representation of the wave function. Actually, this one has a particular name, the pseudo wave function. However, the representation of the pseudo wave function is quite great with the same number of grid points now, right? So, TFT people are really smart, aren't they? Okay, let me summarize now the 4 steps to get a pseudo wave function. Step 1, calculate the Kohn Sham wave function in presence of the core electrons. This wave function is typically referred to as the all electron wave function. Okay. Step 2, decide on a radial cutoff RC. That is the radius which sets the boundary of the core region where the wave function is to be modified. As shown in this figure, we'll call the interval 0 less than r less than RC as the pseudization region. Step 3, inside this pseudization region, replace the all electron wave function by a smooth and nodeless function. For example, a simple polynomial. Now finally, the 4th step, that something you need to check. The new function that has been chosen, it should yield the same electron density as the all electron wave function for 0 less than r less than RC, that is in the pseudization region, and also it should match the value at r equal to RC. Okay, well, I guess now we do have some idea about how to get and what actually is a pseudo wave function. But then, what is a pseudopotential? The question still remains, right? The pseudopotential is actually the potential which, if plugged in into the Schrodinger equation, will provide the pseudo wave function as a solution. Or simply, the potential associated with the pseudo wave function is called the pseudopotential. Mathematically, if we call the pseudo wave function as UP and the pseudopotential as PP, then the Schrodinger equation will be minus h square by twice m d square dr square UP of r plus PP of r UP of r equals to EP of r into UP of r. Or we can also say BP of r equals to EP of r UP of r plus h square by twice m d square dr square UP of r whole divided by UP of r. Or finally, BP of r becomes simply EP of r plus h square by twice m d square dr square UP of r divided by UP of r. By the way, as we have said earlier also, one may also choose not to use the pseudopotential, and then that calculation will be called all electron calculation. But this is rare. Most of the DFT works nowadays are carried out by using pseudopotentials. Ideally, a pseudopotential is developed by considering an isolated atom of one element. But the resulting pseudopotential that you have got by the calculation can then be used reliably for this atom in any chemical environment without further adjustment of the pseudopotential. This desirable property is referred to as the transferability of the pseudopotential. Current DFT codes typically provide a library of pseudopotentials that includes an entry for each, at least most elements in the periodic table. I feel you are already having a sense that now you are quite smart fellow in DFT. You may feel smarter then by knowing that there are different types of pseudopotentials. The details of a pseudopotential essentially define a minimum energy cutoff that should be used in calculations in which the atoms associated with that particular pseudopotential is involved. For example, I am opening a pseudopotential file for you. See here, minimum E cut rho and minimum E cut WFC is clearly mentioned for that particular atom. Similarly, for all other pseudopotential files, there remains the suggested cutoffs that should be used in the calculations. Now, pseudopotentials requiring high cutoff energies are said to be hard pseudopotentials. while more computationally efficient pseudopotentials with lower cutoff energies are called soft pseudopotentials. The most widely used method of defining pseudopotentials is based on the work by Van der Velde. These are called the ultrasoft pseudopotentials or USPPs. As we can guess from their name also, these pseudopotential files require substantially lower cutoff energies than alternative approaches. One disadvantage of using ultrasoft pseudopotentials is that the construction of the pseudopotential for each atom requires a number of empirical parameters to be specified. But guess what? If you are going to use a DFT package and you are not in the research of developing pseudopotentials itself, you don't need to worry about this particular disadvantage. Current DFT codes, which you are actually going to use, typically only include ultrasoft pseudopotentials that have been carefully developed and tested. But they do, in some cases, include multiple ultrasoft pseudopotentials with varying degrees of sharpness for some elements. Another fusion core approach that avoids some of the disadvantages of the ultrasoft pseudopotentials is the projector augmented wave or PAW method that was originally introduced by Bloch and later adapted for plane wave calculations by Crisci and Jobert. Crisci and Jobert actually performed an extensive comparison of ultrasoft pseudopotentials, PAW, and all electron calculations for both small molecules and extended solids. Their work shows that the well constructed ultrasoft pseudopotentials and the projector augmented wave method give results that are essentially identical in many cases. And as importantly, these results are in real good agreement with all electron calculations. Though, in materials with strong magnetic moments or with atoms that have large differences in electronegativity, the PAW approach gives more reliable results than ultrasoft pseudopotentials. Now, one example of a hard pseudopotential is a norm conserving pseudopotential. As the name suggests, it tries to keep many norms of the all electron wave functions unchanged, or it respects the norms of the all electron wave functions. For example, the total charge of the all electron calculation and the calculation that is using a norm conserving pseudopotential is identical. But that conservation of norms comes with a cost, a higher cutoff energy. Even if just one atom in your calculation is hard, a high cutoff is required. This translates into large CPU and RAM requirements. That's why ultrasharp and PAW pseudopotentials are much more popular. Though, while doing optical calculations, it is always advised to use the norm conserving pseudopotentials. In my description box of this video, I am providing some really good websites for getting different types of pseudopotentials. Okay, thank you all. I believe that this lecture had been quite long enough, but also you have learned many things here, right? Okay, let's meet again in our next video. Thank you. Thanks a lot.